Hi everyone, we are Team Wakanda, and our presentation today is about Dysarthria speech reconstruction. I'm on the team with Pris Muvunyi, Ememune Zero, and Seth Abayo, and our team mentor is Talha. The ability to speak and speak clearly is crucial, but not everyone has that privilege, and not every speech technology affords everyone that privilege. Our problem. The problem is about dysarthria speech. And dysarthria speech is a multiple speech disorder caused by muscle weakness in breathing muscles used in speech production. This is usually a result of diseases like ALS or cerebral palsy. This is significant because most speech technologies remain sensitive to dysarthric speech. This is mainly due to the fact that the models behind these technologies are usually trained on normal speech and just noisy speech. The task is generally divided into two main categories: voice conversion, technique to enhance dysarthric speech, and the construction of a text-to-speech system. This can be seen on this diagram. You have your dysarthric speech, you pass it into a feature structure. This gives you your spectrogram that you then pass into a transformer-based speech to text, which is specifically what we use. In our case, which is web to vec. This will give us transcriptions that we can then pass to a text-to-speech that will give us high intelligible speech. So our work is focusing on the part of the recognizer in order to be able to get accurate enough transcriptions. There are not many publicly available database for dysarthric speech. From the few that are available, we chose the Togo database. This has 15 speakers, where 8 of them are the ones with dysarthria speech. More details about Togo can be found in the table below. So the Togo database is actually very small. It only has like 23 hours of English speech data. And this it has limitation. First of all, it does not have interspeaker variability, and also it's just short recordings of speakers. So it's not a conversational type of speech, which is the one favorable for speech recognitions. So to tackle that, we applied the segmentation, the two main ones being pause insertion and speed alterations on the clean speech.
As mentioned, we used Wave to Vec as our ASR model. The reason for this is it being state-of-the-art and open source, meaning we could fine-tune it and accustom it to our data set. As mentioned, there was not enough dysarthric speakers to accommodate for a good enough model. So we modified the healthy speakers dataset and applied some data augmentation to replicate the dysarthric speakers, so we can increase our dataset and be able to train on more samples. Upon extracting those spectrograms, we passed them into our ASR model, extracted the transcription, and then from those transcription, you can then pass them to a text-to-speech model that can provide intelligible speech. Our metric was the word error rate, which is the addition of the number of substitutions, number of deletion, and number of insertions over the total number of words in a reference text. The original base Wave to Vec was trained on the TIMI dataset and provided a 32 word error rate, while ours was a 0.75 error rate. The reason for this was that it performs better on the sentences, but performs poorly on single words. These are references, and thank you for watching our presentation.